That's a very nice applause. Thank you very much. Let's start. Lieber Herr Professor Meschede, liebe Professoren Hofferbeet, Jean-Michel Raimond und vor allen Dingen auch lieber Professor Markus Aspelmeyer, begrüße Sie sehr herzlich im Namen der Alexander von Humboldt Stiftung. Humboldt, Jens, ladies and gentlemen, dear guests, welcome to the Bonn Humboldt Award Winners Forum. It is a great pleasure for me as a representative of the Alexander von Humboldt Foundation to welcome you most warmly to this forum that takes place, as always, in Bonn. Our Secretary General, Enno Aufderheide, has asked me to address you on his behalf. He, all of a sudden, needed to rush to Berlin for a press meeting with our president, Professor Robert Schlögl, who also extends his best regards. It's all about funding for the Alexander von Humboldt Foundation that we receive from our ministries. And he, of course, would have loved to meet with all of us, but decisions about funding are taken in political Berlin. With the lasting tradition of 11 years now, the Award Winners Forum addresses a different discipline each year. This year, however, this statement is not quite correct. We already held an Award Winners Forum on physics, on quantum physics, exactly 10 years ago. Already at the time, the event was organized together in close cooperation with Professor Dieter Meschede, chairing the scientific committee this year as well. Having the pleasure twice, lieber Herr Meschede, this is really very great. Thank you for your constant, continued cooperation. The applause is more than deserved. And there is a second thing I'm very pleased about. The fact that the opening ceremony of our Award Winners Forum is taking place here in the Wolfgang Paul Lecture Hall of the University of Bonn. Wolfgang Paul, I should tell, our foreign guest, was president of the Alexander von Humboldt Foundation between 1979 and 1989. 1989, he was awarded the Nobel Prize. When I joined the Humboldt Foundation in 1991, I still had the pleasure to work with him as our then honorary president. So I well know how much he shaped the foundation with his ideas and his generosity. It was a time when Germany became reunited. And when I joined the foundation, I felt who is the president or the honorary president at the time, because there was a very demanding discussion about whether we should sponsor Germans in Germany. It's against the mission. The mission of the Humboldt Foundation is to invite exclusively scientists and scholars from abroad to Germany. But he says, of course, this is right. But we need to think about that this is a historical singularity. And those who wrote about the mission, they never expected Germany becoming reunited. So we started a special program to sponsor scientists and scholars from the then German, eastern part of Germany, in the so-called western part. This was Wolfgang Paul, very original, very innovative, and very strong also in his argumentation. He was a strong advocate of our principle quality over quantity that still shapes and guides our foundation and as also the selection of our grantees. This is also the reason why all of you, the award winners and fellows, are together here today. In 2001, the foundation awarded a one-time Wolfgang Paul Prize to outstanding scientists and scholars from abroad. It was intended to give them the opportunity to conduct research as freely as possible. The award gave us also the freedom to try something new. Even though the prize was only granted once, to 14 scientists, it became the pathfinder in the development of the Alexander von Humboldt professorships we are granting nowadays. I'm very happy that one of these 14 scientists, Atak Imamoglu, participates in this forum today, or at least tomorrow, when giving the talk. Participates in this forum today or tomorrow, and this will be the opportunity to also share his views about what has been the difference between the time then and nowadays. As I have already mentioned, Wolfgang Paul's generosity. After he was awarded the Nobel Prize, I already mentioned, he donated a large part of the prize money to the so-called Wolfgang Paul Foundation that is administered by the Alexander von Humboldt Foundation. Money that finances, for example, the Wolfgang Paul Lecture, which brings international outstanding scientists, physicists to Bonn. Among them have been Richard Taylor, Stephen Chu, David Wineland, Wolfgang Ketterle, each of whom being Humboldt Research Award winner as well as Nobel Prize winner at the same time. This year, Pierre Agostini, another physicist of the Humboldt family, was honored with the Nobel Prize. He received a Humboldt Research Award in 2003. So it takes you 20 years to get a Nobel. Sometimes 15, sometimes 10, but very often 20 years, roughly. Think about Ferenc Krauss, who is also one of those 2023 Nobel laureates in physics, is also closely associated with the Alexander von Humboldt Foundation as an academic host and a reviewer. So who knows if we won't be able to celebrate more Nobel Prizes at the next laureate forum in physics. Wolfgang Paul, however, was not only president of the Humboldt Foundation, he was primarily an outstanding physicist, sure. This was not only evident in things like his inventions and publications, but also in practical life. I'm a living witness to an outstanding success, a very special outstanding success of Wolfgang Paul at one of our foundation's summer parties. Already honorary president of the foundation at the time, Wolfgang Paul won what is called the cherry pit spitting contest. Kirschkernweitspucken auf Deutsch. He was the best. As he said, he had analyzed how he was to shape his tongue to achieve the greatest possible width, and his analysis was proven right by his success. We were all beaten by a Nobel Prize winner. I think there's at least one person, Gisela Netzke, in this room who can testify that it's true what I'm telling you here and I'm sharing. So Wolfgang Paul was a true Humboldtian. Humboldtian not only in his connectedness with the Alexander von Humboldt Foundation, but also in his admiration for the ideas and ideals of our namesake. Just as Alexander von Humboldt, he recognized the value and benefit of networks and trust. Networks that bring together different ideas, visions, and backgrounds and allow them to grow into something new, something with which solutions are sought and found. And of course, this is also the idea for our award winners forum today and the next days to come. To connect observations, to connect ideas, to connect people. Alexander von Humboldt had realized how important it is to create space for debate and exchange between colleagues when, in 1828, I would like to remind you, he went to great lengths to organize one of the largest natural scientists conferences of his era, the Assembly of Natural Scientists and Physicians. About 400 scientists and physicians from all over Europe came to Berlin for the Congress. Our forum is not quite so all-encompassing, but it brings together young researchers, mainly Humboldt Fellows, with our award winner, senior, globally renowned capacities in their field. And I encourage you to make the best use of this space for debate and exchange. And here I address particularly the young researchers. Please seize the occasion and get into contact with your experienced colleagues. For them, meeting with you means meeting with the future of their research fields. And that's finally why they came here. So you need to prove their intentions as well. Before I wish you all an inspiring conference in the spirit of both Alexander von Humboldt and Wolfgang Paul, it is time to give thanks. First of all, to you, the members of the scientific committee, Dieter Meschede and Sebastian Hofferbert from the University of Bonn, and Jean-Michel Raimond from Sorbonne Université. Without you, the members of the selection committee, this event would not have been possible. I'm deeply grateful for the wonderful scientific program you have really designed and created with your dedication to bring this possibility for exchange and debates to life. I would also like to give gratitude to the rector of the university, Michael Hoch, who would have definitely been with us. There was a really complication because just 2 hours ago, the academic year of the University of Bonn officially was opened in the almost neighboring building. So one should not do sessions like this, forums in parallel, but there was no way out because of the time schedule. He promised, however, to join us this Friday for a plenary discussion. So I think we are in good ties with the university, doing something which is actually not allowed, I wouldn't say, but not very much welcome. And with this gratitude, I would like to hand over to Dieter Meschede as the representative of the scientific committee. Thank you very much. And I wish you all inspiring days together with your colleagues here in Bonn and in Siegburg. Thank you for your attention.
Yeah, what can you say? Welcome again from our side, from the organizing committee, but also on behalf of the University of Bonn and the physics department. I think our chairman should also say a few words, but I'm afraid he's tied up in meetings. And so I will try to replace him and say a few words to you. Thank you very much again. This is the Wolfgang Paul Lecture Hall, and maybe I should say for me it's in a twofold way interesting. Wolfgang Paul actually was essential because he was the one who made sure that this lecture hall was constructed. He loved what he always called physics for the heart. And so this is what you see actually in the background. So this is obviously mechanics for the first year students. And so we have a very nice collection here. And I think that's one of the very nice things that we can show to the students. And I would also like to give a warm welcome to the students who have found their way in here to hear about, later on, about gravity and quantum physics and other things by Markus Aspelmeyer. Yeah, the other point is that maybe I can share a personal note on Wolfgang Paul with you. In 1989, when he was indeed the president of the Humboldt Foundation, I traveled together with him and Ted Hench to Saudi Arabia, to Riyadh, where Ted Hench was awarded the King Faisal Prize, which is considered the Nobel Prize equivalent in the Islamic world. And so ever since, I think, this was the time when I got to know him, and ever since we were in close contact until I somehow ended up here in Bonn or so. And so, as you see, there's a lot of things of interest in this case. Our meeting is centered around quantum physics, maybe ultra-short pulses and other areas. Wolfgang Paul is an interesting figure because I think he is really at the borderline also. He was a physicist interested in atomic physics. The famous Paul trap was his invention in the early 50s, which is now a very widespread instrument in atomic physics. By the way, it was more than in the first part directed towards accelerator physics and particle physics in terms of a mass filter and other aspects. But he is really a good figure in this sense that he was really at the borderline of two parts of physics. This, in terms of our physics department here in Bonn, has carried on into these days in the spirit that we have a large particle physics community here and also quantum optics and what we call atomic, molecular, and optical physics community, which has tremendously grown over the past, let's say, 10 or 20 years or so. Okay, so let me also thank from our academic point of view the Humboldt Foundation. So it doesn't happen all that often that somebody tells you, well, why don't we collect all the people you are interested in from around the world for a workshop, and you just tell who you would like to have here, and then we'll take care of the resources and everything. So thank you, and dear colleagues and friends, I think we should thank the Humboldt Foundation with an applause for that. In my personal view, the Humboldt Foundation really plays an enormously important role in our outreach of science into our international community. I believe this is the most, from my point of view, is one of the most important, let's say, cornerstones that we have to build trust in our colleagues from other countries, because it's directed at persons and not at projects. We have lots of projects going together, but I think that in terms of trust, the most important thing is really about persons and individuals. And I think this is at the forefront of what the Humboldt Foundation is indeed doing. And I just learned from Steffen Mehlich that apparently the president and the general secretary had to go to Berlin to talk about funding. I personally find it very sad that our foreign office, the Auswärtiges Amt, decided to cut down. This is owned by the Auswärtiges Amt, the German Foreign Office, and to cut down in funding for the Humboldt Foundation and, as importantly, on the Goethe Institutes. I do not believe that our administrators know what treasure we have in this. Okay, with this, I think I would still think, let us enjoy this meeting. I'm very pleased that you have found the time and made the efforts to all come here. Let us have a very nice and exciting and inspiring scientific meeting. I look forward to it, and I think we should now go to the first opening lecture on science by Markus Aspelmeyer, chaired by my dear colleague Jean-Michel Raimond from Paris. Thank you very much.
Okay, thank you, Dieter. I should mention that most of the work in the program committee was done by Dieter. It's obviously a privilege and an honor for me to open this first session of the Humboldt Symposium, particularly in this beautiful amphitheater. And the talk of tonight will be given by Markus Aspelmeyer from Vienna University, professor at Vienna University and scientific director of the Institute for Quantum Optics and Quantum Information. Markus has a very bright academic career. He started with a PhD in Munich with Peisel, and then he switched to Vienna to work in the group of Anton Zeilinger, who won the Nobel Prize last year. And he stayed in Vienna pursuing a very original and very fruitful line of research. Whereas most of people involved in the quantum start with one atom, possibly one photon, and try to combine them in more and more complex quantum systems, Markus takes a different approach in which he takes grains of dust, macroscopic specks of matter, and cools them to incredibly low temperature to unveil their quantum behavior. It's very fruitful. It leads to tests of quantum mechanics, tests of gravitation, and I think it's why what he will address in tonight's talk, a very intriguing title, by the way, How to Avoid the Appearance of Classical Words in Gravity Experiments. So, Markus, the floor is yours.
Thank you so much, Jean-Michel, for this wonderful introduction. So I was told by Dieter, my job tonight here is to entertain you. So this is this is what I'm trying. So I'm a member of the Humboldt family now also since many years, and it's really fantastic to be here again. I've been at the meeting 10 years ago to see old friends. Within and outside of the Humboldt network, esteemed colleagues and the next generation. It's really, I think this is exactly what these meetings are for, so thank you very much for bringing us together. Jean-Michel, you already pointed out correctly that the title of my talk actually does not have the word quantum in it. So basically, it's a quantum conference, but I try to stay operational. Essentially, this summarizes the question that we are addressing right now in our laboratory in Vienna, namely, when we want to do gravity experiments, why do they need to be classical? And how would we actually avoid them to become classical when we start quantum? And then, so this is another way of putting that is, of course, you could also basically say, how does a quantum object gravitate? It's a shorter title, but I think the first one is more insightful. So let me, since we have a very broad audience, set the stage with a historical remark. Let's go back around 120 years or so in time. Quantum physics has just started. The success story is slowly rising with the description of atomic phenomena, but Maxwell's equation is still the thing you use when you want to describe the state of light interacting with the atoms. And then came 1905, Einstein's famous paper, here we can see it, on a heuristic viewpoint concerning the creation and transformation of light. It's a beautiful paper. In particular, this goes now to the next generation. You have to definitely read that. In this paper, Einstein conjectures, based on thermodynamic arguments, the existence of quanta of light. And the argument is a really beautiful one, a very simple one. Actually, what he looks at is how, let me see how that works. Does it work? Oh, sorry, just a second. What he looks at is actually how the entropy of the radiation inside, now you see it, no you don't, I don't see it. Wait, there it is. Okay, very good. So what he studies is actually how the entropy of the radiation inside a certain volume changes inside a container with black body radiation when you change the volume of the box. And what he finds out by simple arguments is essentially that the entropy scales exactly in the same way as you would expect from the ideal gas. Basically, Boltzmann's constant times the logarithm of the ratio between the volumes to the power of something. And if you now simply compare the exponents here, you can see that those two expressions are identical when the number of n of non-interacting identical particles is equivalent to this expression, the total internal energy divided by Planck's constant times omega, which lets Einstein to conclude that monochromatic radiation of low density behaves thermodynamically as if it consisted of mutually independent energy quanta, which is really a beautiful argument. And it did not resonate at all with the scientific community. No one liked it, no one accepted it, no one adopted it. So let's have a look at the literature at the time, 1909. So this was 4 years after Einstein's paper. Planck, the rejection of Maxwell's electromagnetic waves seems to me to be a step which, in my opinion, is not yet necessary. 1916, Millikan. Einstein's bold, not to say reckless, light quantum hypothesis flies in the face of the thoroughly established facts of interference. And indeed, 3 years earlier, Sommerfeld actually had derived a formula for the photoelectric effect based on a semi-classical theory, so not using any use of quantum physics for light. Bohr, 1925, so it's now 20 years after Einstein's paper. Even if Einstein sends me a cable that an irrevocable proof of the physical existence of light quanta has been found, the message cannot reach me because it has to be transmitted by electromagnetic waves. So this was 20 years after. Now you would say, well, but we have experiments. No, later on, so we had the lamp shift, G-2, and so on. So we have effects, phenomena, where we need quantum electrodynamics to describe them. Well, it turns out that this was actually not fully the case. By the 1960s, famous Ed Chains from the Chains-Cummings interaction had established a theory, a neoclassical theory of radiation that would, this was the plan of this theory, actually explain all of the existing effects that were described back then by QED already, just with his new neoclassical radiation theory. Then came the famous Rochester 72 conference. So the question that was out there now was, can we have an experiment whose outcome cannot be described by assuming quantum theory on the one hand and Maxwell's classical theory of electromagnetic radiation on the other hand? So assuming that both are true, we use Maxwell for light, we use quantum for matter, and can we have an experiment? So Chains claimed that this was not the case. So here's the quote from back then. At the Rochester conference, Chains goes on record saying, "Physics goes forward on the shoulders of doubters, not believers, and I doubt that quantum electrodynamics is necessary." And it was John Clauser at that conference who calls the bluff and basically accepts the challenge to perform exactly such an experiment. Experiment whose outcome cannot be described by using a classical field theory for radiation phenomena. And the famous experiment was the one here. This was basically a 2-photon atomic cascade experiment where by doing correlation measurements of the 2-photon state behind beam splatters, he was able to violate a Cauchy-Schwarz inequality, demonstrating, so a Cauchy-Schwarz inequality that was bounded by the behavior of waves behind the beam splitter. So essentially, when a wave hits a beam splitter, it is split, and you have a probability that both detectors click. When a particle hits the beam splitter, it won't be split, and that results essentially in a Cauchy-Schwarz inequality. And then later on, of course, there have been other beautiful experiments also by Philippe Grosjean, Alain Aspect, and then later there were the Bell tests that essentially also tell you that there's no classical alternative for quantum electrodynamics theory. So this story is essentially now closed, but note, it was 70 years after Einstein's light quantum hypothesis that we had the first unambiguous experimental test of this conjecture. Okay? So, fast forward today. What about today? Well, today We have quantum theory. It works still. So there's no doubt that we have beautiful experiments. I highlight here a wonderful one from Vienna from my colleague Markus, who uses these huge macromolecules to show large-scale quantum interference. So basically showing that the superposition principle is valid on the level of individual macroscopic particles with 10 to the thousands, tens of thousands of atoms. On the other hand, we do have a theory that describes gravitational phenomena perfectly well, namely Einstein's general theory of relativity. We also know that that works. Best example, obviously, is the recent discovery of gravitational waves and many other phenomena up even in the nonlinear regime of the field theory. So we have now a situation where, again, we have two theories, a quantum theory and a classical one, that peacefully coexist. The current state of affairs is when you do experiments in the, let's say, gravity experiments using, for example, quantum systems, then the following holds. All experiments that we have to date, gravity experiments, so at the interface, all experiments that we have to date can be explained by assuming the joint validity of quantum theory on the one hand and general relativity, which is a classical field theory to describe gravity on the other hand. So this is like the historical analogy now. Let me give you two beautiful examples. This is a very famous one. This is one of my favorites. The so-called cow experiment after the initials of the authors, Colella, Overhauser, and Werner. You have a neutron interferometer that was pioneered by Helmut Rauch in Vienna and Sam Werner at NIST, which is basically a slab of a silicon single crystal where by Bragg diffraction, if a neutron comes here, this first thing here acts as the first slab acts as a beam splitter. You have transmission, a Bragg diffraction. The second one acts as a mirror. The third one, you re-interfere again, and you have a fully closed interferometer for massive particle for neutrons. What happens now when a neutron traverses in a gravitational field, so you have a massive particle going through a classical external field, the gravitational field, quantum mechanics 101 tells us the particle acquires a phase, a dynamical phase when it traverses through the field. How do we measure it? Well, we cannot measure absolute phases, so what we need to do is we need to measure phase difference. So we take the neutron, we split the wave packet of the neutron in an interferometer, and let then the two branches of the neutron wave packet traverse through two different heights in the gravitational field. So while they go through a gravitational field, they pick up two different dynamical phases, you re-interfere them, you pick up the phase difference, and so when you rotate now your interferometer in Earth's gravitational field, depending on the angle, you pick up a different difference in the gravitational potential, and you get gravitationally induced interference fringes at the outcome of the neutron interferometer. So it is a beautiful example how Earth's gravity impacts the wave function of a particle in the quantum regime. Another one, also well known, but I just show it because it's so nice, is gravitational redshift, where you basically have on this table here an atomic clock, optical atomic clock. You measure a certain frequency. So here, if you run in your clock, you measure a certain frequency, then you lift the whole optical table by 30 centimeters back in that experiment, and you suddenly see that the frequency in the experiment jumps, and showing you that you are actually sensitive to the shift of the clock frequency in Earth's gravitational potential on the level of 30 centimeters. Nowadays, when you look into the lab, there's just been a recent demonstration in Junyi's lab at Schiller. We are now at the level where we are sensitive to 1 millimeter scale height differences in Earth's gravitational field, impacting the frequency of atomic clocks. So these are just two examples where gravity interacts with quantum systems in a way where I can, in order to describe the experiment, assume that I can use quantum theory to describe my quantum system, and then just add a classical gravitational space-time geometry on top of it. Basically, what I'm doing is quantum physics in curved space-time, if you want. Which brings me back now to my historic example. I just rephrase it and we go to another conference. There's always one specific conference where things are actually then being spelled out. This is the famous Chapel Hill conference, also called GR1 conference. And the question is very similar than we had asked before in the electromagnetic case. So we have now the coexistence right now experimentally between quantum theory and our classical theory of gravity. So it's very fair to ask the question, since right now no experiment requires a quantum description, do we actually need a quantum description of gravity? Or in other words, can we have an experiment whose outcome cannot be described by the joint assumption of quantum theory on the one hand and Einstein's classical field theory on the other hand? And this is exactly what has been discussed at this 1957 conference, where Gold, an Austrian physicist, asked exactly the question, so can we have phenomena which the classical theory of gravity is unable to explain? Feynman was also there, and he gave this in his typically inimitable answer, right? Yes. But he also, of course, gave a Gedanken experiment to make his point. The Gedanken experiment is a nice one. Feynman actually said, so think of the following. Think of, well, here's instead of a beam, just think of a particle. Okay, a massive particle, let's say with a spin inside. And the particle interacts with a certain device. And this device, if you think that the particle has a spin, let's say 1/2 somehow internal degree of freedom, you let it fly through a Stern-Gerlach in the Stern-Gerlach device, then the particle wave packet splits up and you create a superposition of the particle going up and the particle going down. Right? So this is now our mass, our source mass S that can be in one of the two positions. It's in a superposition in up or down. Okay? Now assume you have a second particle sitting next to it, and now you switch on gravity. Okay, what happens? Your first particle, this one here, the source mass, is in a superposition. The test mass here sees a superposition of gravitational fields, and so that means what happens now, over time, you see the two branches interact at different accelerations with our test mass, and after some time, also the test mass will evolve in a superposition of positions. You correlate now the two positions and momenta of the two particles into what we call an entangled state. So now, if the evolution is long enough, you will actually generate now correlations between the joint positions of the particles, which means you get entanglement. So in other words, if I create a mass in a superposition, then if quantum mechanics is quantum theory holds, and the superposition principle also applies to gravitational fields, then we will generate entanglement between the two masses just through gravitational interaction, which is totally trivial from a quantum physics point of view. The problem comes from a gravity point of view. In gravity, what our classical field theory of gravity tells us, whatever mass configuration I have, and so now we look here at this size, here the source mass. I put a black box around the source mass. Whatever mass configuration is in my black box will create a well-defined space-time geometry, within which my test mass follows a well-defined geodesic. If my test mass follows a well-defined geodesic, it will never evolve into any superposition. It will just follow a well-defined geodesic and will never become entangled with my source mass. So a classical, in other words, the state of the field of a mass in a superposition is not a valid solution of a classical field equation. From the point of view of general relativity, the generation of entanglement, the possible observation of entanglement, is inconsistent with the assumption of a fixed spacetime metric, a fixed spacetime geometry. It's as simple as that. There's a fundamental inconsistency that the one is a classical theory and the other one is not. Okay, that's it. That's the whole point. So what Feynman has done now is he has described now a possible experiment that cannot be explained anymore with our current classical theory of gravity, which is a classical field theory described by Einstein's field equations. So, the next step is, of course, so further in the conference, there was also Louis Witten, the father of Ed Witten, and he asked the most important question. He asked the question, what prevents this Gedankenexperiment from becoming a practical experiment? Yeah? And this is going to be the rest of the talk. This is the question I would like to, let's say, ponder a bit about with you. Okay? Is it sort of, can we fantasize, and if we do so, with some back-on-the-envelope estimates, is it in principle possible to do such an experiment? So, if you look in the literature, ever since Feynman's Gedankenexperiment, nowadays we have a couple of actual more, let's say, mature suggestions how one could do that, and essentially it falls into two categories. Category number one is, I just take two masses and I treat both of them as harmonic oscillators. Okay, when you have two harmonic oscillators that are coupled with each other, to each other, let's say with a 1/r potential, then what happens that those two masses, well, they evolve, they get coupled, you get a normal mode spectrum of the two, and if you now look at quantum harmonic oscillators that are coupled to each other, they will simply become entangled. For the quantum optics community, what essentially happens is you have your 1/r interaction. If you Taylor expand the 1/r interaction, you get to first order an XX interaction, which is a two-mode squeezing interaction. And so what you generate is with two harmonic oscillators coupled via 1/r interaction, you generate a two-mode squeeze state. So it's an EPR entangled state in position and momentum. So this is, and of course, once you have that interaction, you can compute the rate at which you generate that entanglement. This is one possibility. Take two harmonic oscillators, two quantum harmonic oscillators, and just let them interact gravitationally. How hard can that be? Then the second possibility is, start with like Feynman-like idea of having a mass in a superposition of a macroscopically distinct, of two macroscopically distinct center of mass states. Meaning, I prepare my particle just like Feynman suggested in a superposition of being here or here, left or right. So I have two macroscopically distinct center of mass states, and I do that with both particles, both with my one, which I called the source mass before, and with the test mass. If I look at this, they are initially also just separable. It's just two superposition states in the center of mass. But now I switch on gravity again, and now what I get is actually what we had before in the cow experiment. You have cow phases now. Because actually this particle evolves in time in the gravitational potential of that particle. So I get now a dynamical phase, and what I get is now actually I get a dynamical phase, the value of which is conditioned on whether I'm in that state or in that state. So this is now a phase evolution that is conditioned on the state here, which is in quantum information we know that as a C phase gate, a conditional phase gate. And if the phase is exactly -1, so it's exactly pi, then you have a C sine gate, and this is when you generate maximal entanglement between your two qubits, right? And that's exactly what we have. If you let this thing evolve in the cow phase, then also after some time you get an entangled state. The fun thing is, even though those two geometries or experimental architecture sound very different, if you compute the rate at which you generate entanglement, it's the same. It's this expression here. So the rate at which they couple, at which you generate entanglement, is the ratio between these two numbers, Newton's constant and Planck constant. Mass square, because, well, you have a gravitational interaction. The delocalization square. In a way, it's like it's driven by the amount of delocalization, and the delocalization in that case is defined by the distance of the two center of masses in your superposition, and in that case is defined as the width, the delocalization of the wave packet of your harmonic oscillator, and 1/d cubed, which is the first non-trivial term in the Taylor expansion that I told you before. That's it. So it makes sense. And now in order to generate entanglement, that rate, of course, has to be larger than all the decoherence rates in the system. Easy, no? So you say, well, okay, but I have that. So, I mean, if I go to Sebastian's labs, then I have atoms. So I take two atoms, they sit next to each other, I let them interact gravitationally, hooray. I'm done. And then I still measure entanglement, but that's also trivial to do that. So let's look at the numbers. If I take two atoms, I separate them by a micrometer. Okay, and I have like my spread of the wave pack is 100 nanometers or so. So and they're separated by a micrometer, and then I ask, how long does it take now for them to become entangled? Well, as you can see, it's like 1 million times longer than the lifetime of the universe. So it's not a very practical experiment. So the question was, is an experiment in principle possible? Yes. Is it in practice possible? No, if you take two atoms. So then let's not take two atoms, let's take two lead spheres. Okay? Two lead spheres, let's say 50 micron in size, each of the spheres. That's, by the way, so that's the mass is on the order of the Planck mass then, approximately 10 to the 18 atoms now per mass. And you separate them by 100 micron. Yeah, by 100 micron, because I'm talking separation of the center of mass, so they better not, well, move into each other, right? Also, again, here I assume that I can generate a wave packet, so a delocalization on the order of 10 to 100 nanometer. And then I ask, well, how long does it take for them to get entangled? And you see, I get 10 milliseconds. That's not so bad. When you're an experimental physicist and your back on the envelope calculation gives you a time scale smaller than a second, then you at least show some level of excitement, happiness. This is like that's the rule of thumb. Yeah? Smaller 1 second, yay. Yeah? So it makes sense to continue. Okay, so let me rewrite this thing now. So instead of the rate here, the occurrence rate, I basically say, look, it just means that I now talk about coherence time. Okay? So basically my coherence time needs to be long enough. I introduce coherence time, and then basically I can rewrite what I just told you in a very simple condition. So the necessary precondition for doing all of these experiments, if you really want to think about generating entanglement by gravity, you need to fulfill this condition. Mass square, delocalization square, times the coherence time, times d to the minus 3, so the distance of mass, needs to be larger than h bar over g. This, if you don't fulfill that, don't even think of starting this experiment. Okay? If you have something in mind, first check whether this is fulfilled, and then you can continue. Okay, the beautiful thing about that expression is now you can separate that. You see, this one here, this you can check in quantum experiments. Okay? So basically the task number 1 is now do quantum experiments where you maximize the mass times the delocalization times the square root of the coherence time. And this you can even do with a single particle. Okay? Just do quantum experiments with single particles and just look how large you can get that number. This is task number 1. Task number 2 is do gravity experiments, okay? And see how small you can make the d. Because, so this is the question, how close can you actually bring two particles and still make sure that gravity is the dominating interaction? So you really want to bring them very close because your coupling goes up. You want to maximize the gravitational coupling. Okay, so this is why your d needs to be very small. But on the other hand, when you make d small, other forces start to play a role. So you need to make sure in gravity experiment, you need to make actual gravity experiment where you know that gravity is dominating and where your d is small. So now basically, so the task is now make a quantum lab, make a gravity lab, and just crank these numbers up and don't have the labs talk to each other. And then see, the task of both labs is maximize, and then at some point you bring them together, and then they have to find a way to basically, well, combine it. So I took the liberty to give you a very, very rough estimate now in the next 3 slides. I make that quickly. This is more for the experts, but I cannot resist. Just to make again, this is all just back on the envelope. So there are 3 considerations that enter now from the experimental side. Consideration number 1, the lab shakes. Everything is shaky, everything is sort of noisy and so on. It's like, this is a nuisance. And typically, you know, all the atom physics people here in the audience, right? You can all sleep well, because you have a single atom. And a single atom, if you cool it to the ground state, you have a wave packet size, like 100 nanometers, right? Your lab basically shakes like, let's say, I don't know, a picometer or so, right? 10 picometers, you don't care, because your wave packet is 100 nanometer. Right? If your lab shakes a little bit, who cares? Right? Now I come. Right? So now comes my 10 micron lead particle. Okay, I cool it to the ground state. My wave packet size is a picometer. Okay, and now my lab shakes by 3 picometers. You know what happens? This is problematic. So the fact that you now work with more massive particles means you're much more sensitive to these sort of fluctuations that a normal AMO experiment you typically wouldn't worry about. So here, the challenge number 1, displacement noise. And essentially, what you want to do is, you see typical displacement noises in the lab actually scale dramatically with frequency. Okay? So what that tells you is, if you want to do an experiment on a time scale that is longer than a second, okay, you better be ready for an experiment that is not so sensitive on displacement noise. Because displacement noise is large at small frequencies. You really have to put in LIGO, for example, gravitational wave detectors, they put a lot of money and effort to isolate, to basically diminish this noise terms. So let's avoid that work, or at least minimize that work, by saying, well, how do we avoid it? Well, we just start working here, okay? Let's say we only start working here. How do we do that? Well, we never measure longer than 10 milliseconds, let's say. So we fix our measurement time, full stop. So don't even think about measuring longer than a second. But I want to be on a conservative side. I would say 10 milliseconds is fine, so let's stick to that. This is a conservative assumption. So this means now we have a bound on the coherence time. So it's just through experimental considerations. Next consideration, electromagnetic shielding. This is really subtle, because obviously you want to have an experiment where you isolate gravity in the presence of electromagnetic interactions. Even if you remove all charges from your objects, you will still have some dipole moments inside. I remember a breakfast with Arno Rauschenbeutel like 10 years ago, I think. Right? And I was like, I was enthusiastic, telling him about his ideas, and always when you discuss with Arno, it takes like 2 minutes and it destroys every idea you had. No? And I think this was already my 3rd minute. I was very good this time at that breakfast. And then Arno was like, yeah, what about dipole coupling? And I was like, because even as, so now I'm using it for my talks, you see, so thanks for the input. So even if you don't have any charges, you still have some internal moments, okay? And they will couple, full stop. So you need Faraday shielding. There's no way that you will be able to do a gravity experiment without shielding electromagnetic interactions. Yeah. So, and again, look here, d to the minus 3. So we need to be very close. So we need a shield. We need to go very close to the shield, like only, well, as close as possible. The question is, how close can we get to the shield? Current experiments, so we have the famous Erdwash gravity experiments. The smallest distance today in a gravity experiment between 2 masses with a Faraday shield, where you're sensitive to gravity only, is the one by the Erdwash group, where they are on the order of 50 micrometer. Okay, and so what they do is here, they place the Faraday shield here between the 2 masses, and in their case, they use like a 10 micron thick beryllium copper membrane. They gold-coat it, and so on. Our goal is, and we are building an experiment right now, to go to 10 micron. Okay, so this is what we want to do. We want to do an experiment where the distance between the two surfaces of the masses is on the order of 10 micron. Eric Adler is helping us with that. I told Eric we're going to go below 10 micron. Eric says that's impossible, and so we fixed our bet at 10 micron. Okay? So everything up to 10 micron, Eric wins. Everything below 10 micron, I win. But conservatively, I of course believe the people who have been working longer in gravity, D naught will be limited to 10 micron. This is our second working assumption. You need a Faraday shield, but if you have one, you will never go below 10 micron. Okay, full stop. We just believe this to be true. Which bounds now our D, also experimentally. Okay, last one is now the challenge of decoherence. So when I have a superposition, a center of mass, sitting in front of a conducting Faraday shield, if it's not a perfect shield, if there's some if you imprint some memory, so to speak, in the shield, so if you have some losses, then you will get decoherence. And here the working assumption is, to first order, decoherence scales with some order of the separation, delta x, divided by the distance, the ratio of delocalization over the distance. Which means you get now an additional, and so that means you want to have, in any case, your delocalization much, much smaller than the distance to your Faraday shield in order to minimize decoherence, which now is the third boundary condition. So now we have three conditions that bound by experiment delocalization, coherence time, and distance, which means now, and all of that are actual numbers, okay, backed more or less by more or less reasonable assumptions, which means now we have a limit on the mass. Okay? So that means now, if you just rewrite everything I said, it means that the mass in your experiment cannot be smaller than 10 to the minus 6 times the Planck mass. Okay? So remember, Planck mass is 10 to the 18 atoms approximately. So in order for these experiments with the boundary conditions, with the, let's say, reasonable experimental boundary conditions I gave you, there's no way that you can do this experiment with masses smaller than 10 to the 13 atoms or so, or 10 to the 12 atoms. So you need to shoot for that. You already know now that in your quantum experiments, you need to have masses larger than 10 to the 12 atoms, and in your gravity experiments, well, this is the value you sort of should push for. Yeah, or at least it should be, well, somewhere between 10 to the minus 6 and 1 times the Planck mass. Christoph. So Casimir is, in that case, simply an electromagnetic interaction. So there will be always an interaction between, there will be always an interaction between the mass and the shield. Okay, always. Which means there's a bias. However, what the shield actually does is, because it generates mirror charges, also for the Casimir interaction, what the shield does, it removes the position dependence of the interaction between the two masses. And this is actually the entangling part. This is a DC bias. The shield transforms electromagnetic interactions that are distance dependent into a DC bias of electromagnetic interactions. It's there. Okay, so there will be some additional effect on that, some global phase evolution or so, but it will not generate entanglement in case of a perfect Faraday shield. Thanks for the question. Okay, so here's now basically my summary. This is our challenge. So what we now have to ask ourselves, can we have quantum systems as sources of gravity? Which means, how small can we make a source mass in gravity experiments? We know that it can be larger than 10 to the 12 atoms, but, well, given the fact that doing quantum experiments is hard, it should not be too much larger than that. And on the other hand, and again, remember, gravity experiment really means you need to isolate gravity. You need to be sure that gravity is the dominating interaction. This is the actual difficult part. And on the quantum side, how massive can we make a quantum system? Can we go above 10 to the minus 6 AMUs and still have, can we go above 10 to the 12 AMUs and still generate sufficient delocalization in the center of mass degree of freedom? Okay. So, this was the introduction. Part 2 comes tomorrow at 6:30. Huh? No? Okay. I tried. So, let me tell you where we are right now, okay? And then I stop. So where are we? So let me first start with gravity. So now I cannot switch that off. Sorry. Just a second. I need to overrule now my. I cannot overrule it now. Oh, now I can. Ha. Yes, did it. Okay, very good. So, gravity. You know, typically when you measure gravity, you either have a pendulum on the right side and a mountain. This was how it was done in the old days. Or you have large masses in tabletop experiments, Cavendish-like, where you measure gravitational attraction in the lab. But this is kilogram masses. So what we wanted to do, we asked the questions, how small can we go? And we started with something that sounded easy. We thought, well, so why don't we take like millimeter-size objects, like a small gold sphere? Gold sphere, this is the advantage that you can shake it. And if you shake it, then you generate gravitational acceleration at the location of a second mass, and this you can then easily detect by some optical measurement. That was the original idea. We wanted to do some optomechanics experiments. Well, to make a long story short, we decided later then to do actually a torsional pendulum experiment, and if you do, again, a back-on-the-envelope calculation, if you have a mass, like a millimeter gold mass is like 90 milligram, you shake it, okay, so you modulate its position by a few millimeter, so basically you go from minus infinity and you go towards the test mass to about 400 micron or so to surface distance, and you go back, then the acceleration modulation at the location of the test mass is on the order of 10 to the minus 10 meters per second square. Or if you convert it in displacement, that's a few nanometer displacement of this pendulum here, okay? Now, the problem is, of course, if you just have such a pendulum like that here on the right side sitting in your lab, well, of course it shakes just by the fact that this is a regular basement lab in the Vienna downtown, okay? And you can see here at the data already that basically you see here the data is quite noisy. This is during the day. Then the data becomes less noisy. Do you see that? The variance is smaller, it becomes less noisy, and then you see the bump. You see the bump? Another bump. It's a bump, another bump. That's the night bus. It's the night bus at the road crossing that is like 70 meters away from our lab at the road crossing Währinger Straße, Nussdorfer Straße. You see? And you see that one? That's a late night bus. So the press was joking when he published the result that this was the most expensive traffic monitoring system in Vienna. So at the end of the day, what we did was, of course, we measured then over Christmas, and basically I don't go into the details here, but what you see here is actually the signal, the gravitational signal of this small 1 millimeter gold sphere picked up by our test mass. And you see the second peak, that's actually a higher order response of the system, because what you do is you modulate a 1 over r potential. So you modulate a nonlinear potential, and so you basically get, when you Taylor expand that, also higher orders. Yeah. So what we are doing now is, now of course we need to go smaller, because this was like 10 to the 22 atoms in a 1 millimeter gold sphere. So the next step is we go smaller. Yeah, so basically, currently we're trying to use that as the source mass. So basically we go down 4 orders of magnitude in size, which then means we are on the order of the Planck mass then for our mass. source mass in a gravity experiment. However, this of course you cannot do in a regular downtown city lab, so we're going underground now. So we have now set up this experiment in an underground lab, which is super quiet. The noise levels that you can see here in the red one, our mine lab, are much better than in the city. You see this one, so these are single traces. This one is an earthquake here, the single one. And you can also see it in the data. This is the pendulum, and then when the earthquake hits, it's just push it. So this is something one needs to take care of. And so the goal is now, you see, this is our source mass. This is now our Planck mass scale mass that we're using in the next generation of our gravity experiments. So on the gravity side, the situation is now like that. You see here our gravity experiments. This is where we have been before. This is where current state of the art was. We have pushed now the mass in gravity experiments down to that scale, and we will be here at the level of Planck masses, hopefully soon, Christmas again, even in a tunnel. So let me make last few comments on the quantum side. Okay, the quantum side is something that we have been, how to say, we didn't know that we were working on it, okay, since a long, long time. What we have been working on since a long time is basically trying to use quantum optical control techniques to manipulate the center of mass motion of solid-state systems. So you combine quantum optics with optomechanics, and with quantum optomechanics, and you can use that to basically manipulate the center of mass motion in the quantum machine. I'll give you one quick example. What we have been doing lately is we levitate a small nanoparticle. You see this like a 70 nanometer particle. It has like 10 to the 9 atoms approximately in it. We levitate that in the focus of a light field, typically a micrometer or so, that to minimize absorption. And when you do that, you basically you use the light focus down, a so-called optical tweezer, to trap the particle. The potential landscape that the particle essentially sees, because it's an induced dipole from the light into the dielectric particle, so the effective potential landscape is just the intensity of the light field. So if you have a Gauss beam, a focused Gauss beam, then for small displacements you simply get a 3D confinement of the particle, and that's how you can trap the particle. We trap the particle in vacuum. What you do is you can actually take the light that is scattered in front, you can extract the X, Y, and Z component of the motion and use that to feed back on the intensity of the light, and that modulates then the frequency, and so you get a feedback loop that stabilizes the particle. You can do more than that. You can actually do that in a way that allows you to measure the position with essentially Heisenberg limit. So what you do is you image the particle in the backplane, and you can do that now in such a way that the product of the imprecision and back action is only limited by Heisenberg's uncertainty principle, which means you essentially have a Heisenberg microscope. Which also means now that you can monitor the motion of the particle with a precision that is given only by the ground state size of the particle. So I can monitor now in real time the phase space of the particle. So I basically now have the quantum trajectory, if you want, of the particle sitting there at room temperature. And of course, once I have its position, I can do real-time feedback to stabilize the particle in phase space with a precision given by the ground state size, which means I can ground state cool the particle. And this is what we have done. You see now, this is actually a picture of a 150 nanometer sized glass sphere sitting at room temperature and cooled down to the quantum ground state of motion. So the motion is not dominated only by quantum physics. And I'm pretty sure all of you have seen the Event Horizon Telescope picture of the black hole, where light is actually going around the black hole. You remember that? Huh? You see? No? Remember? No? Remember? So this is, here you see the difference between quantum and gravity. That's the main message of the talk. Huh? Quantum is green, gravity is orange. Other than that, it's all the same. Okay, now I just need to get out here again. Where is it? Oh. Wait. I want to let you out of this talk, but my mouse doesn't let you out of this talk. Here, now, there you go. Okay, so what we have now is, we have now our particle prepared in a pure state wave packet. Okay? And now what we need, remember, we need to delocalize it. And this is now the state where we are now. This is the stage where we are now. So we need to delocalize it now. Okay? And what you can do is now, because you work in an optical tweezer, you can just switch off the tweezer. Okay? And it just falls, it evolves. Right? And then basically you delocalize the particle. And only in a few milliseconds, actually delocalize it to the extent almost the size of the particle. That's not so bad. Or you could also actually speed up the whole thing and have the particle ride on an inverted potential landscape, for example, and so on. So there are many, many ideas, and this is something that we are following at the moment. Last comment, you say, well, but this is now 10 to the 9 particles. How do you go to 10 to the 15 atoms? Okay? Well, here's a possible answer. Okay, so here's a possible answer is levitate in a different way. So have, for example, a superconductor and levitate a superconductor in a magnetic field. This you can actually do directly in a cryostat, which also has the added value of removing blackbody radiation, decoherence, and so on and so on. And also you can use a superconductor as a Faraday shield, which might have benefits. Okay, so this is what we are doing at the moment. So we have now trapped a 100 micron sized particle. This is approximately the Planck mass, so 15 micrometer radius. We have trapped that at 20 millikelvin in a 20 millikelvin environment. We read it out with a squid at the moment. We also have a superconducting cavity that we use for the readout. And in principle, if we can get the readout good enough, we can play the same trick that we did with our glass sphere. We read it out such that the imprecision back-action product is Heisenberg limited, and then we should be able, simply by looking at the particle, preparing it into in a pure state. So this would be the dream situation. Okay? So this is a first step, and the question is now, can we push it into this extreme? Summary. This is the summary of the decoherence challenge. You don't have to look at all the numbers, but basically what I'm doing is I summarize the first part of the talk where I gave you the numbers. What you see on the left side is the mass, okay? And the delocalization required for the specific mass. And R is just the size, it's just the corresponding radius if I assume a lead density. So let's assume I have a Planck mass object. Then the Planck mass object, I would need to delocalize by a nanometer. Okay? That doesn't sound much. Believe me, it's a lot. So you need to delocalize a Planck mass object by a nanometer, the center of mass, wave packet, and have temperatures on the order of 10 Kelvin in order to avoid blackbody decoherence. Then you generate entanglement on a 10 millisecond timescale, and you can live happily ever after. Or at least then you should be able to generate entanglement on a 10 millisecond timescale. Or you go down to 10 to the minus 4 times the Planck mass, which is a 4 micron sized sphere. Okay? But then you see you have to delocalize by 500 nanometer. Ground state wave packet size is on the order of picometer. Okay? So you see you need now in Christoph's words, you need a squeezing by 60 dB. Exactly. But if we talk about delocalization, it doesn't sound so terrifying, okay? So we need to delocalize by a few hundred nanometer. So this is why, well, the truth will be somewhere here in between. Maybe 8, 10 micron particle or so could be the way to go. Okay, so that's it. I put one last FAQ slide because this is typical questions that come, and I just want to make that point and be very clear about that. So what do we learn or not learn when we observe entanglement generated by gravity? Okay? The generation of entanglement through gravity is inconsistent with assuming that gravity is described by a classical field theory. That's the main message of the talk. Okay, I'm not saying anything else. Goes back to our old question. Okay, can we have an experiment that cannot any longer be explained by assuming quantum theory and a classical field theory of gravity? It doesn't tell us anything about the quantization of gravity. Okay, it just tells you the classical field theory is not the right one. It's highly likely consistent with a linearized quantum field theory of gravity. Yeah? And it excludes by principle all gravitational collapse models. That's what I want to say. Okay, so this is the summary. This is what we are doing. I told you we need to go these two ways. We need to do quantum experiments to increase the mass. We need to do gravity experiments to make sure that we can isolate gravity. And here are two examples where we actually following both lines of research. And at some point down the road, we have to open the doors between the two labs and let the people actually talk to each other. So with that, I thank you very much. I thank my team. This is actually a visit we did at the Einstein House in Kaput, together with the Max Planck for the History of Sciences. And so big thanks to my team and collaborators, and thank you very much for being here tonight.
So thank you very much, Markus, for this beautiful and I dare say very entertaining talk. I think the mission is a full success. I guess we might have questions from the audience. Yes, plenty of them.
If you speak loudly, I can repeat the question if you want.
Yeah, I'll try to speak loud. My question is, of course, it's very beautiful about the real gravity that comes from the Einstein's theory. My question is, are there any benefits in looking into possible quantum mechanical consequences of analog gravities or emergent gravities in non-gravitational systems?
Thank you very much. So the question was, can we have other tests, essentially, other experiments that would tell us something about the quantum nature of gravity? Okay? So I have two answers. One is actually, this is the slide that I didn't show. Thank you. So, there are right now actually two approaches more or less directly targeted towards quantum gravity. So what you can do is you can assume that a quantum theory of gravity exists, and you can test possible consequences at low energies. So in a way, this is not so dissimilar from the EDM experiments in atomic physics, where you say, oh, what if some version of supersymmetry is correct? What would be low energy consequences of it? And I test that then in an experiment by doing some null measurement in a certain type, which does not require gravity measurements. Okay, this is one possibility. The other possibility is what I just said. You directly try to probe gravitational phenomena. The third one, what you were asking, was what about analog gravity? That's certainly also very interesting experiments that tell us essentially whether the phenomena that we get from assuming a certain, let's say, Hamiltonian, a certain mathematical description of the theory are actually really there, like searches for Unruh radiation or so, for example, or for Hawking radiation analog experiments. They are certainly very interesting. I would consider them interesting for testing the mathematical structure and consequences. Of course, they don't test directly gravity. I mean, in the worst case scenario, when you assume a certain interaction, then you test the validity of the consequence, but maybe gravity simply doesn't behave like that. Which is unlikely, but still.
Thanks for the nice talk. So my question is, in the gravity experiments, you have the Faraday cage with gold coating and whatnot, right? So in the ion trapping community, it's been observed that even though how clean you have the gold coating, there is this patch potential fluctuation problem which can be completely independent on the two sides of the Faraday cage, how would this affect you?
Yeah,
and the second question is, what kind of vacuum do you work with? Because if you have a random charged molecule flying by, it would already destroy everything.
Mm-hmm. Thanks. Thank you very much. To your first question, it seems it always boils down to eating or drinking, because I remember very vividly the last discussion I had on the topic with Rainer Blatt, actually at a buffet in Munich, where we were discussing exactly that, how close can they bring an ion to a surface, and all the patch potential effects. They will be there. The question is the fluctuations. Okay, so again, this is similar to Christoph's question. What you want to guarantee is that you don't have any residual direct interaction of the nature of electromagnetic nature between the two particles. So the patch potentials in the gravity experiment, so this 50 micron experiment that I showed you from the Seattle group, the Earthwash group, they really saw in the experiment when they brought the masses more close than 50 micron to the shield, the signal would just completely go haywire. And they assumed that the reason was that actually they had mechanical vibrations of the Faraday shield with respect to the mass, such that you have effective patch potential fluctuations. And so that is something that we hope to minimize through going to our mine, which is extremely stable. So then the question is, where do the fluctuations eventually come from? So we need to check it experimentally. I fully agree, this is right now biggest question mark. Okay. Second point, vacuum. What we want is essentially that within the 10 milliseconds, that I said, we simply want to have the probability that the particle is hit by something is smaller than 10%. And if you do the numbers, of course, for it scales with radius square. Okay, for a Planck mass particle, you would have to have a vacuum level on the order of 10 to the minus 17 millibar, 17. Okay, this goes down a little bit. If you go to 10 to the minus 5 Planck mass, you're down at 10 to the minus 15 or so millibar that you need. These are values that are demanding, but they exist in experiments worldwide. Thanks for the question.
Yes. Very nice talk. I had a question about the quantum part of your talk, where you propose to delocalize the particle by switching off the dipole potential. Is there any way to probe that you have delocalized the particles before you did the actual gravity experiments to test that you actually have a quantum delocalized state?
Thanks, Martin. Here's the answer. There's another slide that I didn't show. This is an experiment we're working on right now. I give you the gist of it. The gist is so how do you test? Okay, how do you test that you have now delocalized in a coherent way? And the simple answer is, well, you do an interference experiment. Okay, so let's say very loosely you could say a double slit experiment is actually, or let's say an experiment with where you send your matter wave through a phase grating is actually not a double slit type experiment, but it's a test of transverse coherence of your wave packet. So what we want to do is we have a protocol that consists of. So where's my, it's back, you see? So here, you prepare your particle in the ground state, okay? You delocalize it by basically switching off the potential, okay? So you see in phase space now, it gets delocalized, okay? So you get a nice squeeze state in that case. And then the question is now, how do you prepare a grating? Because the problem is, this is a 10 to the 10 AMU particle. So if I just take now a phase grating made of a standing light wave, it won't do the job. Because the phase modulation is just lambda. Lambda is on the order of, let's say, half a micron. and this will not give you enough separation that on a reasonable time scale, before the particle falls to the center of the Earth, you will resolve any interference fringes. So you need a better idea. So regular matter wave interference doesn't work, Talbot-Lau-like and so on. So the idea is the following. Have your particle interact with a nonlinear potential. So if you now have, let's say, a cubic pulse, so a pulse with a cubic intensity profile, okay? So a pulse with a cubic intensity profile that interacts with your particle, what happens? The cubic, the pulse, the light interacts with the wave packet and basically just serves, imprints a phase that is proportional to the intensity of your light pulse. So, and that you have to take now modulo 2 pi. So what you get now is, depending on the strength of your intensity gradient in your cubic potential, you get a 2 pi phase modulation across the wave packet with a periodicity that is much, much smaller than the wavelength of the light. So what you can do now is you can generate essentially a phase modulation across the wave packet with a periodicity given by picometer, if you want. Okay? And then if you just let that evolve, you have now a phase modulation of your wave packet, you let that evolve, and that generates then, that turns into interference fringes in space. This is the super fast way through. So the point is, we do an interference experiment, and we have a protocol that does that, and it's actually, it's adapting ideas, what people already do in electron interference. So this has been done with electrons already. So we are adapting it now to the level of our large particles.
So if I understand correctly, you plan to do gravity experiments at distances where gravity has not been tested. So the gravitational force could have the usual form or not. So for the fun of it, let's just assume for a second that it's not. Would that impact your experiment?
Oh, actually, it would make it more easy, because if it would go as people would expect. So you know, there's this. I'm pretty sure there are people in the audience that know this much better than I do, but in the high energy, or in the particle physics community, there are conjectures coming from, there's a so-called swampland program with some dark dimension and so on, and there are conjectures that at these length scales, gravity should be modified in a way that it becomes stronger, and that would help. Okay, so that would be a benefit, because it means I'm not only scaling by d to the 1 over d cube, but even stronger, so actually I can do it faster. So that would be super cool, because this experiment would go faster. Less vacuum problems, requirements.
Thank you very much. And so I'm wondering, how can we make sure the given state, the state created in your laboratory, is really entangled? For instance, in standard way is you do the state tomography, and then based on the data, you try to apply, I don't know, PPT criterion or something like this. Either you could apply CHS inequality or entanglement witness, whatever you like. But if I understand that correctly, you apply some criteria which is based on distance and massive, and assuming the state is pure, maybe. But okay, in our reality, the state is always mixed. So how can we, again, so how can we really make sure the quantum state is really entangled?
Well, so in the end, it's going to be an EPR type experiment. So as I said, if we now stick to actually having 2 harmonic oscillators, so if you say we have now here, we have 2 harmonic oscillators, okay, that are coupled now via 1 over R, then you would expect them to become entangled in an EPR manner. So that means that the product of the conditional variances of momentum and position would violate a Heisenberg uncertainty. principle. So this is one way of phrasing it. This was like Reed and Drummond EPR criterion, has also been experimentally tested exactly in that way by Kimball, for example. But there are now more, let's say, evolved entanglement criteria, witnesses, but in the end, it all boils down to being able to measure locally for each particle individually position and momentum, and then correlate those measurement outcomes. And then you do have witnesses that can tell you whether you are entangled or not. And this is also what we are doing. What you see here is we actually have charged particles. So those two particles are now just charged. You see here with like 100 charges on each of the particles. So we have now a Coulomb 1/r interaction. And what you see here is actually the normal mode splitting of the two coupled harmonic oscillators. Yeah, and in principle, you could say now, so this is now classical, but the ground state of that normal mode coupled system would already be an entangled state. Yeah. And so this is something what we are trying right now, basically show how to do it with Coulomb entanglement, that we learn exactly that.
Thank you.
Just a second, Markus Aspelmeyer, please stay with me. Just a second, please. I also would like to say a few words of thanks to our distinguished speaker of tonight. Thank you very much for this truly inspiring talk. The many questions made it clear that the intrigue was a very nice one. So, and always, or sometimes, we've even presented the answer without knowing about what is going to be asked. This is really perspective, intriguing. I want to say you're not only an award winner of the Alexander von Humboldt Foundation, but also an active honorary service to the Humboldt Foundation. He is member of the selection committee for the Alexander von Humboldt professorships. I already spoke about this, the continuation, if you can say so, of the Wolfgang Paul Prize. So responsible for selecting those Alexander von Humboldt professors in any of the fields, not only in physics, even not so much even in physics. So I would like to present you as a token of gratitude of the Humboldt Foundation and of all the people here in the room, the invention of nature. This is a, I would say, scientific biography of Alexander von Humboldt by Andrea Wolf. So something you would not need to shield off, you can just touch and read. Vielen herzlichen Dank.
Danke
Herr Aspelmeyer, wunderbar.
Danke sehr.
Das ist wirklich toll. Schön. Surprise.
Yes, well, surprise. First of all, I'm also very happy to add my welcome to all of you guests from near and far, and also big hi, thank you for coming to the Bonn physics community, where I see quite a lot of faces from very young students to more senior members. So it's nice to see you also mix in here. To make it short before we go to dinner, yes, we have a little surprise. It has to do with this lecture hall. As you have maybe been seeing during the talk, you see many of the beautiful experiments that are performed here in the undergraduate classes every day. And we have many of the standard experiments that maybe you have taught yourself or you have seen yourself in other events. But we actually have one exhibit that's a truly unique museum piece, you would say, a historic artifact that we would be very happy to show you. And if I say we, it's neither any of us would normally teach here, but we actually have 3 fantastic students from our master program who have volunteered to show this to you. Yes? So they have seen this in the lecture, but now it's their turn to teach you something. And before I introduce them and put them on the stage, maybe one quick word also. We've already thanked a lot of people. As always,
behind all the other layers of importance, there are the silent people in the back who do all the work, and that have also been many of our students here. Some of them sit here, Florian in particular, who has been handling all the technology here on the stage. So without them, none of us would be so obviously easy at ease to do these things here. So maybe it's also time to thank them already. And now, in particular, you will meet three of them here on the stage, Valerie Loy, Valerie Maud, and Julia Gamper, who have prepared one specific experiment and also a bit of an introduction to this. So thanks a lot, and enjoy your time here on the stage.
Thank you for the kind introduction. As already mentioned, we are going to perform a little surprise today, which will be in the form of the famous Hertz experiment. So Heinrich Hertz was the first to prove the existence of electromagnetic waves, and with this also was able to prove Maxwell's theory of light back in 1886. This then paved the way to numerous applications such as wireless communication, radar, radio astronomy, and many more. We wanted to show you especially this experiment today because, on one side, Heinrich Hertz was a famous physicist here in Bonn from 1889 on, but also he rebuilt the famous Hertz experiment here based on the original version, which can be seen up there. And now Valerie is going to explain you the Bonn version Hertz experiment in more detail.
So, as already mentioned, this is a setup of the famous Hertz experiment. And here on the right, you can see the dipole consisting of two metal balls, which is powered by the induction coil here on the bottom. And if we now apply a high voltage to these metal balls, we can see sparks between the spark gap. And maybe we'll show you this for a moment. So here you can see the sparks across the spark gap. And those sparks will then generate electromagnetic waves. And the goal of Hertz was then to show that these electromagnetic waves can be detected on the other side. And to do so, the sender dipole is located in the focal point of this parabolic reflector. So this here is used as the parabolic reflector. And in this way, the electromagnetic waves are directed to the receiver dipole, which is located on the other side, so which you can see here. Yeah, we now need to close the experiment and bring the reflectors into position so we can actually show that these electromagnetic waves can be detected with the receiver dipole.
So now to detect the signal, a spark gap on the outside is used. It's here on this side of the experiment. You can also see it up there on the screen. And the two metal parts, this one and this down here, that form the gap are actually connected to the inside, to the receiver. So hopefully when we bring the two parts really close together and send a signal from the emitter to the receiver, we can hopefully see some sparks. So let's try that. So you have to look here. I think we can already see some sparks. Yeah, okay, perfect. So that worked. Yes, so that is the way that Hertz showed that there are actually electromagnetic waves, but he also proved that those waves are linearly polarized inside of this experiment. And he used a polarizer for that, and it's just a wooden frame and some metal strings. And if the polarizer is in there like this, with the strings horizontally aligned, we can still, hopefully, yes, still see the sparks. But if we now rotate it by 90 degrees, the sparks are gone. So that will only happen for linearly polarized light. So yes. He also proved that. Yes, so that was the famous Hertz experiment. And thank you for your attention, and enjoy the rest of the evening.
Yeah, so we are all now invited by the Humboldt Foundation to reunite outside. Everybody here in the room, of course, all of our guests here in the lecture hall, we are going to reunite outside for a reception with a glass of wine, other beverages as well, and something to eat, I hope. Sure. Vielen herzlichen Dank und ja, sprechen Sie mit Ihren Kolleginnen und Kollegen. Do speak to each other, because it's about debate, exchange, and everything else. Super.